Good morning, everyone. With apologies for my camera not working, I'll do the introduction to this seminar. My name is Antonio Gonçalves da Silva, and I am the Executive Vice President of the European Federation of Chemical Engineering, EFCE. I've taken on the role of Executive Vice President in January 2026, following one term as member of the Executive Board of EFCE. I'm a chemical engineer, naturally, by training, graduated from Instituto Superior Técnico, the engineering college of the University of Lisbon, Portugal. And I had an industrial careers in the areas of project, erection, commissioning, and startup of industrial units. And in industry, I also worked in product development, customer service, logistics, quality, and business management. At the same time, I had an academic career for more than 30 years. I was a professor of chemical engineering at the Lisbon Polytechnic, together with the activity in the industry. Finally, in the last 19 years, I had several positions at the Ordem dos Engenheiros of Portugal, the Engineers Professional Association, and lawful regulator of the engineering profession in this country. Two simple conclusions about myself. First, I'm very old. And secondly, I've been very busy. I'm very happy and honored to be involved in the introduction of this webinar on thermodynamics for zero to low emission technologies, mini-series part 1, heat pumps, a long title. Let me say something about the Spotlight Talk series now. This is now our 6th year of the Spotlight Talk initiative, which started in 2020 to keep together the community during the COVID pandemic. The success of the previous years convinced us to transform the Spotlight Talk into a regular feature of the EFCE program. We have now one Spotlight Talk series in odd years and 2 in even years, such as 2026. This spring, 11 of our working parties and sections, namely mixing, multi-phase fluid flow, membrane engineering, static electricity in industry, crystallization, drying, chemical reaction engineering, process intensification, education, thermodynamics and transport properties, and early career chemical engineers are delivering over 2 weeks, 9 webinars of 3 or 4 talks focused on specific topics by leading industrial and academic experts. The series also enables attendees to sample matters in new areas, encouraging cross-fertilization of interests. The complete program is naturally available on the EFCE website. EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 professionals in Europe. EFCE's working parties and section cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of EFCE's activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. Before concluding, I would like to thank all the colleagues who worked hard within the working parties, sections, and wider EFCE for this initiative to happen and be successful. In particular, many thanks to EFCE's Martin Pou in Toulouse, who did most of the conceptual, setting up, and practical activities. Merci beaucoup, Martine. I thank you for your attention, and I wish all the speakers and the attendees a fruitful and successful webinar. I would then give back the word to the chair of this event, Professor Maria-Grazia de Angelis, who's also the chair of the EFCE Working Party on Thermodynamic and Transport Properties, to start the webinar. Thank you all. Maria-Grazia?
Thank you. Thank you, Antonio. Thank you for the kind introduction. I am very happy and proud today to represent the Working Party on Thermodynamics and Transport Properties that just turned 20 years old this year, because it was founded back in 2006. And it has always been at the core of the EFCE and of the Spotlight Talks. So we have always been very active in organizing and disseminating the Spotlight Talks. The aim of the working party that is currently formed by 60 members between academics and industrialists is to create a network of experts to point out needs and issues within our field, identify the priorities, increase the visibility of thermodynamics, and advance some educational aspects, and take away the fear of thermodynamics, which sometimes characterizes the chemical engineering curricula. So in practice, what we do is organize and give awards, both to early career researchers through the Excellence Award, which we award every 2 years to the best PhD thesis in thermodynamics, but we also honor more senior academics by giving the Michelsen Award to a distinguished figure in thermodynamics every 2 years. We organize conferences and events besides the spotlight talks. We are very much involved in the organization of the ESAT conference. The next one will take place in Lisbon in mid-May 2026. And it's a conference that has recently turned 50 years old. So it is a very traditional and successful, I would say, conference. And this year we will organize the IoT, the Industrial Use of Thermodynamics workshop, which is a series of presentations and a roundtable from academics and industrialists. And this year it will be around the themes of circularity and sustainability. We also publish position papers, and we want to emphasize the role that thermodynamics has in these new emerging technologies and in supporting the transition to a clean energy and a clean industry system. We also represent most of the European countries. 1/3 of our members is from industry and 1/3 of our members is female. And I think that's it for me. And I will hand it over to Christoph, who together with Anto has organized the Spotlight Talk session.
Yeah, thanks, Maria-Grazia. Thanks for the introduction. Yeah, my name is Christoph. I'm professor at TU Dortmund University, and I'm the German delegate in the Working Party of Thermodynamics and Transport Properties. And yeah, let's say Anton Tenkate, who can unfortunately not be here today, and me, we from the very first start have been organizing these Spotlight Talks with a big success, and we do it really with pleasure. And we had already many topics that we discussed. For example, also machine learning for thermodynamics, or like what to do with the CO2, capture it, use it. And of course, what drives us thermodynamicists is also how can we contribute in technologies that mitigate climate warming that we already face, like the 1.5 degrees already done. So that's why we thought a little bit, yeah, Antonio's not here anymore, but yeah, it's a big name. So Thermodynamics for Zero to Low Emission Technologies mini-series part 1, heat pumps. So the second part will be coming, but we cannot announce already a title. Anyways, so why did we choose that? Because I think it's very meaningful to combine our thermodynamics experts and to have their view on how heat pumps can contribute and how thermodynamics can contribute to this technology. What is the state of the art? How can we further improve this? And we saw quite recently that BASF company will this year have, together with a pillar company, supply a heat pump that has the function of a heat pump. It does what it should do. So it compresses vaporous waste heat from industrial heat sources and bring it to a usable temperature level. Yeah, so that's what it does. And That systems, to give you just a brief number and then I hand over, will compress around 500 tons of steams per year. So it's quite exciting to see that it really comes to very big industrial processes. I can quickly tell you like that heat pump systems has COP. I'm sure the speakers will tell you what that is, of approximately 3. Will use low heat at around 60 degrees Celsius and put it to 190 degrees Celsius. So that to give you a short appetizer, so what is possible, and I think it's quite amazing what is already possible technically. Yeah, with this short introduction, I want to, before I introduced Professor Bardow, I want to say if you have any questions, you are not allowed to turn on your mic. So all the audience, please use the Q&A. So you find in the bottom of your Zoom menu, you find the Q&A. And please ask or write your questions that you have in that chat. Yeah. And please, as soon as you have a question, write that, right? So don't wait till the very end of the talk. Yeah. Otherwise, we cannot sort it in time. So write it whenever it comes to your mind. So that is my wish list for you. And now I'm very happy to announce the first speaker is Professor Andre Bardow. So actually he's in ETH Zurich, as you can see. I have to be honest, he is very well known. He has a CV. I have maybe read shorter papers than his CV. So it's really impressive, Andre. So thanks so much for being here and sharing your view. So you're actually a professor in energy and process systems engineering, and I'm really very happy to have you here, and I'm looking very forward. And the screen is yours.
Okay, can you see my screen?
Yes.
And you see the pointer?
Yes.
Yes.
Okay, so I could not be happier to be here and the setup is working. So thank you so much for inviting me and for the kind words. I'm excited to speak about this topic because it touches upon things I care a lot about. And one thing is clearly thermodynamics. And the other thing is clearly our climate change, because I think it's really pressing, it's really important. And maybe for a thermodynamicist, heat pumps are really the no-brainer we need to be doing, and we are not doing enough. So I think you quote BASF as an example, that's awesome, but I think we really need to do much more. And so what I try to do with this talk is explain a little bit where I do see the challenges and also the contributions of thermodynamics. And so I titled the talk High Temperature Heat Pumps, taking us from mixture thermodynamics to really net zero heat supply systems. That's what we're looking after. And on the title slide, and this announcement was that I'm the speaker of this, but I have to be honest with you because actually most of what I'm going to be presenting was developed together with Dennis Roscosh, who was a senior scientist in my group and who now took over, is now in industry and taking this really into actions. But I just want to make it very clear that Dennis contributed a lot and it is really a key contributor and he's now really taking into action. Okay, to set the stage somewhat, what are we discussing today? It's about decarbonizing heat. Okay, that's basically the big story. And that's important. And in some way, and at the moment, we are mostly supplying heat by fossil resources, but the idea is kind of clear what we should be doing. Okay, we have now the revolution of renewable energies, electricity, and so we should exploit this renewable electricity to decarbonize also heating. And in principle, there's a couple of technologies out there. And if you open up any scientific journal today, you will see papers on most of them published. And it's awesome that people are working on this. So how can we decarbonize heating? So obviously we can employ heat pumps, the topics of today, but we can also employ directly heating. So really a heating rod, maybe the water kettle that you had at home this morning when you boiled, at least I boiled water for my tea, direct using electricity and heat, as heat, which to many sounds like a thermodynamic crime to take electricity, high exergy, and convert it into heat to boil your water at home. So just to calibrate ourselves, most of us performed a thermodynamic crime this morning. That's why people are proposing other ideas. Let's use this electricity to split water to generate a synthetic fuel like hydrogen or methane, or there's even many more out there. So all these routes exist. What is, I think, one of the beauties of thermodynamics, that thermodynamics can help us to guide us through these different options. And in particular, you can conduct simply energy imbalances and ask yourself, okay, let's assume I'm giving a kilowatt hour of electricity. How much heat can I generate with these pathways? And just to set the stage, and the verdict is very, very clear. Heat pumps really have the beauty that I can take 1 kilowatt of electricity and generate many more kilowatts of heat. And I just put a number in, it's 4. The thermodynamic crime of direct electrical heating at least gives me roughly 1-to-1 heat. It's still exergy loss is enormous, but I get 1-to-1 heat. Whereas by the laws of thermodynamics, if I first need to split water and then burn the water, I'm losing half of the energy roughly. And if I make the chemistries more complex in thin fuels, I will lose even more. And I find this very, very important. And I say it's really stuff I teach in the basic thermodynamics classes, because this is not about people working on hydrogen or synthetic methane being stupid or lazy or so. They just suffer from a route which, by the laws of thermodynamics, has efficiency losses. So this is intrinsic. So for me, the conclusion of the slide is quite simple. If possible, we should employ heat pumps everywhere. That's the conclusion. So if you think about heating, decarbonize your heating, I think your thinking is very organized. Think very hard, can I employ a heat pump? Because the gain is a factor more. And yes, there might be applications where you conclude, no, I really need a fuel, maybe even I need a liquid fuel. Okay, but if you're convinced by this, then you need to pay the penalty of lower efficiency. But otherwise, really go for heat pumps. That should be our priority. And that's why we're pushing the boundaries. Okay, and how are we standing by decarbonizing heating by heat pumps? Okay, for this, I looked, this is Swiss data, but it's basically what's the energy demand in residential and industrial systems? And what you see at home, at least for Switzerland, which is cold today, it's a lot of our energy at homes are used for heating. It's warm water, the shower you had this morning, and it's your heating system. But also industry, actually the majority of energy for industry is used for heating. The catch is, so we know what to do, how to decarbonize this, prioritize heat pumps. And if you look at homes, it's actually kind of awesome that is in Switzerland and many other countries by now, heat pumps are the most sold heating source for private households. The market is established. There's still challenges out there, but it's kind of the go-to technology by now, which is awesome. The story is very, very different in industry. So in industry, yes, we also have some space heating demand, which we could supply by heat pumps, but most of what we are seeing is actually process heat. That means high temperature heat. And if you look what we're doing today, it's basically 100% fossil-based, I would say. So the challenge which I will be addressing in this talk is how can we generate heat pumps that provide heat at higher temperatures to supply industries? And so I mentioned Dennis. I just want to say anything I'm presenting, I didn't do anything except contributing some stupid jokes. So these smart people have compiled this presentation, and we worked with awesome people and got some funding. In particular, I want to highlight the Fachhochschule Ost, University of Applied Sciences, with whom we collaborated on this topic. Okay, so why is it so much more difficult? Why are we lacking heat pumps for industry? And for this, and because this is a webinar of thermodynamics, I have to show at least a stylized thermodynamic diagram where I plot temperature over enthalpy, like a simple diagram for heat for pinch analysis. And in the residential systems, we do have the advantage that all of us are individuals, but actually at home we are rather similar. That is, we like our homes to be 22, maybe somebody likes 25, but the heat we want, our heat demand is roughly at the same temperatures. And also the heat source, okay, maybe difference by countries, but actually when it's cold, not when we start heating, not so much. So we have basically one fixed use case all across humankind. So what we need is we need one type of heat pump that basically takes environmental heat, the heat source, and pumps it up to the heat demand. And for this, we have been very efficient at designing such cycles. Yeah, for the non-thermodynamic experts, I think most of you should know. So this is the vapor dome, two-phase region, and we can design the cycle where we have compression, heating, and expansion, and the heat uptake in here. So we really optimize these systems. That's awesome. Now, if you take a look at industry, the story changes completely. Why? Because the heat demands can be all over the place. They can be at very different temperature settings. You might want to boil some water at 100 degrees. Another company wants to heat up a gas to 200 centigrade. So it's very different temperature levels. Also, what is going on is very different. You might want to generate steam at a certain temperature where the temperature doesn't change, or you take a cold gas and heat it up to feed it into your reactor. So it's both the temperature level and the temperature glides, as we call them. The temperature ranges are very, very different. And the same holds for the heat sources, where at the home we are usually tied to the air, or maybe we drill to the ground, but it's environmental heat. Christoph was mentioning BASF is using some waste heat. They have it 60 centigrade. Oh, maybe your company has something as 80. So we have very different use cases, both on the sink side and on the source side. And that is a challenge. How did we approach it by now? Now we design specialist heat pumps for every single application. So you will find heat pumps out there, but basically if you look at them carefully, you will figure that somebody had a use case where they needed steam at that temperature and had waste heat at that temperature. And so there was a heat pump designed, and now somebody tries to sell it. So we have specialist heat pumps and also specialist refrigerants, that is the working fluids. And that, because we have this, basically, these are not mass product systems, but they are custom designed systems. And that makes them very expensive. Or you misuse them because they were designed for a different case, you lose the efficiency, which is basically the losses are how tightly your cycle is connected to the heat source and sink. So what we have been looking for in our group is to say, can we not find a heat pump that simultaneously covers all of these applications? And the key, why is that, won't that be nice? Because then we can have one design and scale it out to all industry applications. So we can basically generate some economics of scale here, at least of numbering up. And the key is to find the right refrigerant. And the refrigerant we are proposing is not a refrigerant, but it's a refrigerant mixture, okay? So the idea is that you don't use a refrigerant A, but you use a mixture of two refrigerants, components, I call them now components A and B. So what is the idea? We define and we try to look for a mixture A and B, and just by changing the composition, which means I can keep the same seals, I can keep the same materials in my company, but I just sell to different people different mixtures. I can customize the refrigerant, the heat pump, but still generate efficiencies. And this is possible theoretically. So what you see is an animation where we just, and this is literal data, where you change the composition. And what you see on the left-hand side is that basically the cycle is changing completely. I can shift by just changing within one mixture the composition from one pure component to the other. We can shift the levels of the temperature, and you saw we changed the glides. So we started with this idea. We started a project saying, if we could exploit this flexibility in temperature level and in glide, what can we do? We can really make sure that we can tailor a heat pump to a specific industrial application. But basically what will happen is that customer A will get a 10-90 mixture and customer B will get a 70-30 mixture. But still, because we limit to two more molecules we need to deal with. We have still one product platform, you can call it, so that we can benefit also from reductions in capital cost, that we can mass customize at least a slightly tweaking system. The question is, does such a system exist? Because this is a nice animation, but do these refrigerant mixtures exist? And for this one, I just sneaked in, you need to know thermodynamics, because we don't want to try this out. I just want to highlight what Christoph was also referring to earlier. And just if you are scared about thermodynamics, was indicated has been traumatizing for many people. Trust me, it's awesome, and it just got much better and much more convenient to use. And in particular, also we've been benefiting a lot from AI, and this is just a slide on what we've been recently doing. So we've been employing machine learning, but I think the catch is, like thermodynamics, there's always a catch. We really need to instruct the machine learning algorithms. We cannot use them blindly, but we need to instruct them that they speak really the language of thermodynamics by implementing thermodynamic constraints. But now there are also some developments out there. I just want to highlight one thing, what we did in our group. We have a version of PC-SAFT, which is an equation of state. And we have an SPT model based basically on the structure. It's GPT, ChatGPT. And what we can enter any molecule as text, as smiles, and we can predict things like vapor pressure and mixture properties. And this works amazingly well. So what you see is a large database of vapor pressures we predicted. This is a cumulative error curve. The blue line is basically if you fit PC-SAFT. The red line is what our predictions are. It's really predictions. So we have errors around 10%. But which might sound a lot, but just to show you some examples, for some simple molecules, we are perfect. This is an average deviation, which you see is experimental deviations. But even for very, very complex structures, I think we get reasonable predictions with these tools. Yeah, so just please overcome your trauma from your study time and really look at these amazing tools that are out in thermodynamics. A lot of people in the heat pump world believe RefProd is thermodynamics. Trust me, there's more to thermodynamics, and in particular, if you want to go into the world of mixtures and so forth, you have to use these advanced methods, okay? So we use these kind of tools in our group to answer the question, is it really a good idea to use these mixtures with a temperature glide? And this is what Philipp Wiedmeyer did. So what basically he analyzed, is there an advantage to use mixtures? And this is a complicated graph. But basically what he varied is what you see here, is on the x-axis, on the y-axis, sorry, you see he changed how much is, what's the glide, the temperature change we want at our heat sink. Is it none or is it high? And on the x-axis, you see the same thing for the heat source. Do we have a constant heat source or is there also a glide up here? And what we've plotted is the COP, the coefficient of a performance. Again, how much heat do I get per electricity put in, and we compare what is the gain for a mixture. And what you see, this light color or anything green and yellow means mixtures are better. Meaning, if you have an application where you have this temperature change at the heat source and at the sink, you should use a mixture. And the advantage can be 26%, which for industrial applications is a lot. So what we see is this idea, which industry has been kind of avoiding to use mixtures with a glide, would really benefit, help us a lot by giving us almost up to 25% of efficiency gains. But, okay, these are specialist mixtures. So we design for each, this is a grid, for each point we design the optimal mixture using thermodynamics. Then the next question was, do these all-rounders exist, which we have been proposing? So basically, is there one mixture which I just need to tweak and it works in every single situation? And the news is they do exist. So what you see here are a couple of mixtures which we found, and you find here a relative COP, which basically is the loss in COP you have by saying, no, I want to use the mixture of these two components instead of the optimal fluid at this point. And what you see is, yes, you lose a little bit, obviously, because you're not using the optimum, but you do not lose much. You lose a couple of %, and I give a list of 5 mixtures, actually the list is very long, okay? And what you see is, this is the same plot. So you see again the change in heat sink and heat source, and you see how much all-rounder mixture is losing to the best molecule out there. And we see it's actually can cover a large space with almost no losses. So the conclusion is that this concept that we thought about would be nice does exist. Yes, and in fact, there are plenty of mixtures which could provide this flexible design platform for heat pumps and still retain very, very high efficiencies. Now, I've been advertising how awesome thermodynamics and our predictive models are, but still the proof of the pudding is in the experiments. And for this, we collaborated with the Fachhochschule Ost, the University of Applied Science in Ost, who are amazing. And they do have a high temperature setup for heat pumps. You see a picture here, and they generated a lot of data. And actually, I have to say, the companies who provided, in particular, the compressor were scared. So we needed to sign that we kind of waive any liability. Yeah, but it worked like a charm. And now I can tell you the company is Bitzer because they are super proud that basically there was no problems in the operations. And they're super proud about this because our colleagues generated a lot of data. I apologize, it's a little bit complicated, but we see here for different mixtures, again, the COP over the mixture composition. And the main message you should see, these lines all go like this, meaning that mixtures actually do enhance the COP. And this is experimentally confirmed. That is either pure component, they are different, but the maximum performance we actually find for mixture compositions. So yes, mixtures really significantly increase the COP of heat pumps. So we confirmed the first finding, these specialists exist. And then what we found exciting is to analyze the data, but also do these all-rounders exist? And that's a similar plot, but be careful, it's a COP again, but now plotted about the 3 different combinations of heat, sink and source temperatures we had. And I know it's a little bit messy, but I'm just going to be in line. This is basically the same mixture. And it's really that by changing the composition of this mixture, we find the best performance. Obviously, we did not test all the molecules we could check in the computer, but this concept really seems to be working, that by tuning a 2-component, you could call this refrigerant platform to your specific application, you can really get this benefit of COPs. And what I'm really excited about, I cannot fully disclose, is that this will now be industrially demonstrated. I'm not allowed to say the name of the company, but just to say I love Switzerland, because we have now a company everybody of you knows that will build such a heat pump in their operation because they see the benefits of this and they've understood do the heat pumps. Okay, now this is awesome. I'm very excited, as you might figure by now. So did I just solve high temperature heat pumps? Yeah, and for this, I need to be honest with you that I tricked you a little bit with our graphics. What do I mean by this? I plotted this big space of heat pump applications and showed you that in most of the space, we are green or yellow, meaning the mixture heat pumps are awesome. But there are some blue regions where they are not that awesome. And let's look at cases where they are not that awesome. This is the cases where we don't have a temperature glide in heat source and heat sinks. And if you think about this, what kind of applications are we talking? One application is generating steam. If I generate steam at 200 centigrade, it's boiling water to steam, the temperature does not change. So while this space looks maybe small, I have to be honest with you, actually, half of the industrial applications are this class of applications. So what I showed you till now is awesome if you have glides that the temperature is changing, but for steam, actually, this is not the solution. So we have to look for, and I think it's really important to separate these 2 cases, and we have to look at another class of solutions. And for this aspect of steam generating heat pumps, I want to emphasize another point which is important. because it's not enough to design a heat pump, in particular in industry, because actually a company like the BASF buys a heat pump, but it has a lot of boilers. It has a waste stream. It's really, you have to have a heat pump that needs to fit into the energy system. And it's actually more complex than a usual boiler, because a boiler, I just take my fossil fuel and I burn it. But a heat pump, I need to make sure that the waste heat is available and the temperature levels are well aligned, because I'm not burning something to 2000 centigrade, but every Kelvin matters. So it's really, does it fit into your overall energy system, the heat pump? So a standalone analysis of your heat pump is insufficient. So what we did in order to analyze what's the role of heat pumps and which heat pumps do we need to generate steam, we looked at a whole chemical site. And this is been published. This is a typical, archetypical chemical site where we have demands for electricity and for different steam levels, for example. And some of them have a profile over the year, low temperature steam, for example. Some have a constant demand over the year. So, and the question is now not which heat pump is the best one, but it's really what's the best, what's our ambition, net zero energy supply system. Okay, and so we looked at those 4 heat pumps, but we also put things in like these synthetic fuel, these boilers, which might be relevant for the high temperature steam. We did a very detailed analysis. I cannot show all the details, but we developed a model. We analyzed in very many scenarios and very different conditions, but I will just share you the base result finding, because actually they turn out to be very stable. I'm happy to discuss with you. So we analyzed the system. What's the optimal net zero greenhouse gas emission supply system? Yeah, and it looks like this. I apologize, a little bit complicated, but just if you look at the left-hand side, what you see, yes, there's heat pumps, but there's also a lot of other stuff. Electric boilers, even hydrogen boilers. And if you look at the nominal design, the capacities we are designing, basically we cover like half of the capacity with heat pumps and the rest is covered with something else, okay? So you might say, oh, I told you so much about heat pumps and now suddenly it's just half of the cake. So why is the next series is kind of a given? It's hydrogen boilers. Huh? But it's not true if you look at capacities. If you look at energy produced over the year, it's actually 90% is produced by the heat pumps. And it's only the peaks, in very rare utilization, it's 10%. We go either for the boiler, it's even a transcritical heat pump is the red one, I should be honest. So it's only 3% of the energy which is generated by these boilers. So that's really our emergency backup capacities, peakers, because they're super cheap in investment. So I don't want to oversize my heat pump the same as you do at your home. You have a storage or maybe an electric heater to cover this one really crazy cool day per year. Okay, then just heat by electricity. The same thing is happening here. This one crazy day, I will not oversize my heat pumps. So heat pumps is again, it holds even on the systems level what I told you. Heat pumps have the priority, even looking at it economically. And what kind of heat pumps are these? Now I take a zoom into the technology, because this is the heat pump we find, and it's here hidden a little bit complicated. So what we find, it's actually a low temperature heat pump. So to produce high temperature steam, we use a low temperature heat pump. We generate low temperature steam and then do vapor recompression. So the conclusion is actually what we find, and this finding is quite robust, that the best high temperature heat pump for steam generation turns out to be a low temperature heat pump. And still this is important because the heat pump does most of the lifting because you evaporate the water, which is a lot of the energy input. But why do we prefer a low temperature heat pump? Because we find much more efficient refrigerants. And we can operate really a heat pump as its sweet spot, so it's maximum COP. And then we do basically this uplifting with the compression. And we solve 2 problems. At this high temperatures, we find very few refrigerants which would even just work. And what is nice, this technology could be feasible today. Okay, so with this one, I hope I covered the whole space. And I just want to conclude. I hope I could show you that this idea to use mixtures with a temperature glide is really a promising concept to supply applications where we do have temperature glides. Whereas for steam and also high temperature steam is actually best supplied by low temperature heat pumps plus vapor recompression. And I just have to emphasize, money makes the world go round, but if you take a step back, you will find that thermodynamics is really the guiding star that takes us to such analysis. With this, I thank you for your attention, and I'm happy to answer any questions which I don't see.
Great. Thanks a lot, Andre, for this amazing talk. So it was a lot of fun, and we really see that you take it very seriously. And we have several questions. So the first is, it's a very technical one. The first is the heat pumps, those who are implemented in industry, are they meeting their ATEX standard?
Oh yeah, it's for industry actually. We put industry is much more easier, I think, than at home. That's basically the application. Actually, we put this in our design in design optimization. We want to implement these constraints, but industry people kind of told us, don't worry too much.
Yeah. Similar to this, there's a similar question. So there is, could you think of, or maybe you have already done it, to take also into account other criteria, like for example, toxicity, flammability, stability, things like these?
No, it's so yeah. So I've been very thermodynamic that I only showed you COP. Yeah. So maybe let's take the natural next step would be at least money. CapEx, combining basically thermodynamics tell me about operating costs. We didn't look at CapEx. And if you think about a little bit about CapEx, what is the trade-off is always by making the cycle more efficient means smaller temperature differences, meaning larger heat exchangers. Yeah. So there is a trade-off, but I don't show this today, but money-wise, we also see this advantage for heat pumps. It's a smaller number. Yeah, as a rule of thumb, maybe half the numbers I showed you today is the example you lose in economics. Yeah, and then you come to the other properties. Yeah, and yes, we can take them into account, and we do. And for some, we do have models. For some, we just have lists, kind of which molecules you're not allowed to use. Yeah, frankly, I enjoy the liberty of being an academic. Yeah, to still say, if I forget about everything, which molecule would be awesome? Yeah, that at least then I can go to a chemist and saying, this one would really, really be awesome, but it kills the ozone layer, the climate, or the employee. Can we tweak it a little bit, get some inspiration from this? Yeah. So the approach we are literally doing is we usually run it at least once unconstrained completely, and because these approaches are also now computationally quite efficient, and we use this as a post-processing usually, because also to be very honest, if you go into in particular toxicity predictions, all our predictive models are pretty bad. Yeah, and you know that they are because toxicity is the inverse of pharmaceuticals. Yeah, we cannot predict pharmaceuticals well, so we can also not predict the opposite well. So so these things are important, but what we usually do is really do this in a post-processing. You get the long list. I showed you 5 molecules or some pairs. We have a long list, and then we start scratching off, and some of this we automated.
Yeah. There are several ways to deal with it, but I think, you just choose one, and I think that's very reasonable. There's another question. I see there are many more plumping in, but maybe we cannot answer them now. So, Andre, if you take some time during the next minutes, you can also answer them, hopefully by yourself. But there is at least one important one. So, how about the critical point? So, Jean-Charles is asking this because. Like Pisa, for example, is known to fail a little bit describing the critical point. Is that an issue with the heat pumps? So how far do you get close to the critical point? How far is it possible? And give that a big uncertainty.
Yeah. No, it's that's very true. Yeah. So this classical equation of state fail at the critical point. Yeah, but plant operators don't want to operate at the critical point because it's also very nasty to operate a compressor in that region or something. Yeah. So what we see is basically if what we do in all our applications, we imply a safety margin, basically kind of a reduced pressure factor, stay away from the critical point, and it kind of catches two birds with one stone. Kind of, we stay away from the regions where our models suck, but it's also we stay away where we won't. The compressor producer would say, "Don't operate my compressor in that region and other devices." Yeah, so I think it's fundamentally true, and we should get better and so forth. But I think on the practical side, it has not hurt us very much.
Yeah. Okay, there's another question that comes more than one time even. Oh, there are many questions. You will have a lot of fun with the Q&A session, Andre. But we can make one more. So what is an expected COP for your example where you combined the heat pump with the multi-level vapor recompression? So do you know that?
Honestly, I will look it up in the paper before I say something
Okay.
wrong. But
Okay.
it's maybe also I can make one general statement before I say a wrong number. Yeah? But even if your COP is 1.2 or something, yeah, then people say, oh, this is terrible. Yeah. But what is your competitor? Your competitor is at best one for electric heating, or you start doing a syn fuel. Yeah. So if I talk about hydrogen, your advantage is still a factor 2 in efficiency. So I think that sometimes there's a misconception. What I'm seeing is because people get spoiled by their home applications. Yeah, just colleagues have an office building with COP of 10 operating in real life. Yeah, and now I come and tell you in the worst case, but it's higher than that. But in the worst case, very high applications we get lower. But it's you need not to compare to a different application, but you need to say what would be your best alternative. Yeah. So, but I will write the exact numbers from the paper.
Okay, great. Thanks. Maybe the last that we can discuss here before we need to go to the next speaker is, did you touch the topic of centralized versus decentralized heat pumps? So did you find so if so, did you find arguments pro and con?
Yeah. No, so in the study, I looked at the systems. It's basically you'd say it's a combination of both. Yeah, and so there's obviously you do have some economics of scale, but the heat pump sizes are at the moment limited. Yeah, so I cannot buy a heat pump that replaces the largest fossil boilers we have at the moment. So I think that's more the practical constraint. And I think what is really important is maybe from the case study, what we've seen is that you really make sure that you operate at the peak point of the operating regime. Yeah, so basically we use the heat pump to do the bulk at its COP, optimal COP, and then we had peakers to fill it up. So that's what we would typically observe. But I think centralized heating system, yeah, like the city of Zurich voted to ban all fossil by 2040, and the city of Zurich is using the lake as the ETH is using since 1939, the lake to heat its main building. So these systems do have advantages. Decentralized combined with district heating.
Yeah, okay, great. Then I have to correct myself. There's one question that appears now several times, and maybe it's really important to tackle that as well. These mixtures that you have considered, are they also suitable for cooling instead of for heating?
We have not looked at that, honestly, but I would expect that the answer, basically on all what I've seen, is the same. If you have a cooling glide application, yes. If you want to freeze something at a certain freezing point, then not.
Okay, great.
So
okay. Thanks, Andre.
for
Thanks so much. So, for all this discussion and for all your time, thanks so much. So now we come to the second speaker, is Aya Barakat, and she has been doing her PhD in the field of heat pumps, and I'm very happy that she accepted our invitation. She has done her PhD in the Laboratoire Réaction et Génie de Procédés. So that is a research unit that closely collaborates with University of Lorraine and also CNRS. So that is the National Center of Scientific Research. And she did that in Nancy. And now she's working in the company. And her company is the NEEXT Engineering in Belfort in France. And Aya, I'm very happy to have you here. And please share your screen, and then I give the word to you, and then
Thank you very much for
the
the
screen is yours.
invitation. Okay, I'm sharing my screen. So you can see it now.
Give me a second. So it's still trying to. Yeah, now we can see it. Perfect.
Okay, perfect. So, hello, my name is Aya Barakat, and today I'm going to present to you a new type of refrigerants for heat pumps. And these refrigerants, unlike conventional and commonly used ones, are chemically reactive. Andre talked about the power of mixtures for high temperature applications where the temperature of the source and sink are variable. And you can tailor the composition of these fluids to the application. But in this case, the fluid itself is changing its composition because of a chemical reaction inside. So just a little bit of an introduction about myself. As Christoph said, I did my PhD at LRGP under the supervision of Drs. Jean-Noël Jobert and Sylvia Lasala. Now I work at NEEXT, which is a company based in Belfort, France. It was founded in 2022 with the aim of designing and integrating high-efficiency energy systems such as power plants and heat pumps, energy storage as well. So it leads to R&D programs, Sparta and Revolt. And these two are also focused on reactive working fluids. So it is still the same topic as my PhD. And so NEEXT has the exclusive rights to 2 patents that include the reactive working fluids for thermodynamic cycles. And these patents were generated by LRGP. My role at NEEXT is basically includes the calculation of thermodynamic properties for these chemically reactive working fluids at equilibrium. So we don't take the kinetics into consideration for now. Also modeling and optimization of thermodynamic cycles for a different range of applications and clients. And collaborating with LRGP, so it's like acting as a bridge between the company and the laboratory. So first I'm gonna present the motivation and then what we mean by chemically reactive working fluids. Probably it's better if I use the pointer. What we mean by chemically reactive working fluids. And then I'm going to show you the result of using reactive fluids in a heat pump based on 2 studies. The first one is very theoretical, idealized heat pump that is based on the reverse ideal Brayton cycle, and we use the ideal gas law for that. The purpose of this study is to just see how the reaction impacts the fluid, or what does the reaction bring to the fluid. And the other study is more real and in a more realistic cycle, which is the vapor compression heat pump. And in this part of the study, we answer the question, how does the reactive fluids compare to other state-of-the-art real refrigerants for heat pumps? And at the end, I will just present some concluding remarks. So we start with the motivation. As was already mentioned, there's a need to limit the temperature increase beyond compared to pre-industrial levels, so we don't end up with a catastrophic climatic events. And then we know that this increase in temperature is due to the greenhouse gas emissions. And if we look at the sectors that contribute to these emissions, we see that electricity and heat are the first contributor. Now let's talk about heat. The IEA, or International Energy Agency, says that heat pumps or high efficiency heat pumps are the driver for reducing or decarbonizing the heating sector. And this will put us on track for the net zero emissions by 2050 scenario. Now here I present a residential heat pump that is air to water, and this heat pump, as you know, will take electricity in order to provide a heating effect. And of course, it will absorb as well the ambient heat. So usually this electricity nowadays comes from a power plant, and most of power plants are based on thermodynamic cycles. They use thermal sources such as nuclear, solar, fossil fuels. And of course, they reject some heat. So away from just replacing the heating technology with a heat pump, in order to truly decarbonize the heating sector and reduce its footprint, what we really need to do is rely on clean thermal sources and improve the efficiency of both the power plant and the heat pump. So this way we will achieve the real decarbonization and the reduction in the footprint. And the last two, which are the improvement of thermodynamic cycle performance, can be achieved by using high efficiency working fluids, and which is the topic of today. So what are these chemically reactive working fluids? And what we mean here is reactive fluids that are based on the general chemical reaction A2 gives to A. This is a dissociation, association, reversible chemical reaction. So A is a molecule and A2 is a dimer, it's dimer. The forward reaction, the dissociation reaction is on endothermic, while the opposite reaction is exothermic. A very popular example of this kind of fluids is dinitrogen tetroxide, so N2O4, which gives to an NO2. And you can see here the reaction. In this figure below, you can see how the temperature increase drives the reaction. So at very low temperatures, you have almost pure N2O4, which is colorless. And as the temperature keeps increasing, the reaction moves forward to a new equilibrium and produces more products, which is NO2. And at the end, at 50 degrees, you have a mixture of N2O4 and NO2, which is brown in color. So the thing is, these reactive working fluids, they incorporate chemical reactions that happen spontaneously as the temperature and pressure or thermodynamic state of the fluid changes, leading to a new equilibrium. As this new equilibrium is attained, we have a new equilibrium composition, of course. So it's like a new fluid at each equilibrium. Okay. So how does the reaction progress in different components of a thermodynamic cycles? And here I present 4 components that are building blocks of any thermodynamic cycle, I would say. And at the beginning, we have a process which is a heat exchanger, where the fluid is gaining heat from an external thermal source. In this kind of process, the temperature increases significantly usually, while the pressure can be assumed constant. We have a pressure drop, but it's usually insignificant. And so the reaction, how does it move? We can conclude this from Le Chatelier's principle. So it will move in the direction that opposes the change on the system, and the change here is the increase in temperature. So it will go in the endothermic direction and absorb heat. And in the case where the heat exchanger rejects heat and the temperature of the fluid decreases, the reaction will go in the exothermic reaction, providing heat and to counter the temperature drop. Now, when it comes to the compressor, in this kind, in this kind of devices, you have the pressure increasing, and so the temperature follows. Now, the temperature increase and the pressure increase, they push the reactions in opposite directions. But we have seen that usually the temperature effects wins on dictating the direction of the reaction. And for the turbine, it is the opposite, and the exothermic reaction takes place. Okay, so we have an endothermic in compression, exothermic in expansion. So why reactive working fluids? Well, this and the slide, I'm gonna explain the initial motivation behind using the reactive working fluids. And here we consider a compressor and turbine. So for the compressor, you have the inlet that is fully defined, 1 bar, 300 Kelvin, with an outlet of 5 bars. Now, using just the ideal gas law, we can do a simple calculation to calculate how much compression work is required if we were to compress pure fluid A2 and pure fluid A, so without a reaction, the dimer alone and the monomer alone. We can do the same kind of calculation for the turbine, and we take at the inlet, for example, 5 bars, 700 Kelvin, and at the outlet 1 bar, and we can calculate the expansion work generated by pure A and pure A2, and then we can compare. So the conclusion is that the more complex molecule, which is the dimer A, is better in compression, while the simpler molecule, which is A, the monomer, it is better in expansion, it generates more work. And so usually in current power plants, it is impossible to compress one fluid and expand another in a single thermodynamic cycle. However, if your fluid is reactive, there's a chemical reaction inside, and this reaction takes you from A2 to A spontaneously, then this is definitely possible with reactive working fluids. Okay, so the first kind of results are part of the study done during my PhD on a heat pump that is based on the ideal reverse Brayton cycle. And so this is a heat pump totally in the gas phase. You know, this is why we have a turbine here and not a valve. You are used to seeing a valve. And we put a reactive fluid inside. You have a heat source and a heat sink as well. And so we can see how the chemical reaction takes place inside the heat pump. We saw that the compressor, the reaction is endothermic, and then in the heat exchanger where the fluid rejects heat, you have an exothermic reaction, and in the turbine you have an exothermic reaction as well, and in the heat exchanger where you absorb heat from the heat source, you have an endothermic reaction. And what does this mean? It means that here, for example, in the compressor, the fluid acts as an internal cooling mechanism for the fluid, which absorbs heat because of the reaction and cools down the fluid. And this is really favorable for a compression because it decreases the compression work. So other than the compositional effect when going from A to A2, we have other thermal effects that are beneficial if we use reactive working fluids. And in the turbine, we have an exothermic reaction. So within the turbine, the reaction acts as an internal heat source, heating up the fluid throughout expansion. And when it comes to the heat exchanger, where the fluid rejects heat to the sink, you have an exothermic reaction, which means that the reaction is releasing heat, but also the fluid's temperature is decreasing, so it is releasing heat because of the temperature decrease as well. So you have two modes of heat exchange with the heat sink. And the same also happens on the heat source side, where the reaction absorbs heat and the fluid absorbs heat in the form of increasing its temperature. Okay, now for the sake of presenting some results, we take an example, and this is like a simple example. The heat source is taken at a constant temperature of 10 degrees Celsius. The heat sink is taken at a constant temperature of 50 degrees Celsius. Now, these temperatures can be representative of some residential heating application. And so we have 1 bar and 5 bars as the cycle pressures, you know, because we're using also the ideal gas assumption, so to pick reasonable pressures. For the heat exchangers, the pinch point temperature difference is 5, and from this temperature difference, we can calculate the temperature at 1 and at 3, which are the inlet of the compressor and the turbine. Now, what is the thermodynamic model? As I previously mentioned, it is based on the ideal gas law. So we model the system as a mixture of A and A2, and the composition of this mixture at any TP set is dictated by chemical equilibrium. So here you can see the equation to calculate the chemical equilibrium, and you can express it in terms of partial pressures, and not fugacities because it's the ideal gas. And at equilibrium, the constant can be calculated as a function of the entropy, standard entropy change of reaction, and the standard enthalpy change of reaction. Okay. What about the molecules that we consider in this kind of calculation? We have A and we have A2, but what are A and A2 in this case? So we take A to be a monoatomic gas, which is fictive theoretical, and A2 is a diatomic gas, which is also theoretical. And the following are the properties of these molecules. Molar mass of A is taken at 1, and A2 is 2 grams per mole. The Cp and Cv molar are calculated using the energy equipartition theorem. They are constant independent of temperature. The initial number of moles of A2 is 1 mole, while that of A is 0. And the stoichiometric coefficient can be concluded or deduced from the chemical reaction here. Now, instead of fixing one and studying one fluid, we decided to study a wide range of working fluids, and each one of these fluids in the range is characterized by a unique set of the entropy change of reaction and the standard enthalpy change of reaction. So the properties of A and A2 molecules are the same. In terms of molar mass, Cp, and the initial number of moles, but each fluid is characterized by a unique set of the entropy change of reaction, enthalpy change of reaction. And for this application, we consider the ranges of 0 to 0.2 kilojoules per mole Kelvin for the entropy, and 0 to 200 kilojoules per mole for the enthalpy. Now, what do these parameters affect? They affect the chemical equilibrium constant, so the composition, of course, and also they affect the reference state properties, which can be calculated based on this kind of equations. Okay. So the calculation procedure is that we have our thermodynamic cycle with the input given. For each TP condition inside the cycle, so 1, 2, 3, 4, we calculate the composition using chemical equilibrium calculations. And then when we have the composition as well as T and P, we can calculate the total thermodynamic properties, in this case, the ideal gas mixture thermodynamic properties, such as enthalpy, entropy, and we can calculate the specific work and heat quantities and the coefficient of performance. Now, before I show you the results, I'm just going to show you how the results will be presented in this format. You will see color maps in the following slides. On the x-axis, you have delta RS, which is the entropy change of reaction, and on the y-axis, you will have the standard enthalpy change of reaction, which means each point in the color map is a unique working fluid in our case. Okay, and on the top left and bottom right corners of the color map, you can see inert fluid A2, so this is pure dimer, and pure monomer on the bottom right. Why do we get these pure dimer and pure monomer? Because for these fluids, the chemical equilibrium constant is either too low or too high, so the reaction basically doesn't take place. And you will see also a blank space in the color map, and this blank space presents the fluid which are not suitable for the heat pump application, because if we do the calculation, we will find a power cycle and not a heat pump, and this is probably due to the pressure values selected that they are fixed. On the color bar, you will see the calculated property. So at the beginning, I present to you the compressor and what the reaction brings to compression. And the compressor is a very important component of the heat pump. So if you remember, we have the inlet of the compressor that is fully defined at 5 degrees 1 bar, and the outlet of the compressor, only the pressure is defined. You can see that we can calculate the composition as the molar fraction of the dimer at the inlet of the compressor based on the chemical equilibrium constant at T and P. And so we can also calculate the total number of moles, the change in the total number of moles between the outlet and the inlet. So we can see here that for the medium or in the middle of the color map, you have a positive change of the number of moles, which means an endothermic dissociation reaction takes place, while there's a very small zone where the opposite reaction takes place, and in the spaces where the color is yellow, we have zero. So the reaction doesn't really take place here for these kinds of fluids, okay? And now the temperature at 2, it is calculated for all the fluids, and of course the chemical reaction is going to have an impact on this temperature. At the reaction is endothermic, it absorbs heat. And so for the reactive fluids which witness an endothermic reaction, the temperature at the outlet of the compressor is lower than that of inert A and A2 because of the reaction, which means for the same delta P, the pressure ratio, the delta T is lower for chemically reactive working fluids. So you approach isothermal compression. When it comes to the work of the compression, the fluids that are characterized by a low and endothermic reaction also have a lower compression work requirement. Now for the isobaric heat rejection, where the fluid gives the heat to the heat sink, we can calculate also the inlet composition, and we can see that the reaction for the majority of reactive fluids, or all of the reactive fluids, is actually in the exothermic direction. And T2 was calculated and shown in the other slide, but I presented here for the sake of clarity. We can calculate the heat, specific heat. So this is per kilogram or gram rejected to the heat sink. And you can see that for the fluids where T2 is not high because of the endothermic reaction in the compressor, you don't reject as much heat as A2 or A inert without the reactive fluid. But this doesn't mean that the reaction itself penalizes the heat rejection, because if you look at the delta N plots, you can see that the reaction, when it takes place, it increases the heat rejection to the sink, so it provides more. Now in the turbine, we can also do the same kind of analysis. We have the composition at the inlet, and we can see that the majority of the reactive fluids undergo an exothermic reaction, increasing the temperature at the outlet of the turbine. So you can see T4. For a lot of reactive fluids, it is higher than A2 and A, which means for the same pressure ratio, you have a lower delta T also in the turbine, so the turbine becomes more isothermal. Okay, and for the expansion work, you can see that the expansion work is really high, especially if you start with inert A at the inlet, because we said before that A is better in expansion, A2 is better in compression. And you have also a mild exothermic reaction. So this increases a lot the expansion work. Now, what happens to the overall coefficient of performance of the cycle? As you can see here, I plotted the coefficient of performance and the second law efficiency, and you can see that for reactive fluids, you achieve extremely higher coefficient of performances compared to A2 at 2.7 and A at 2.1. However, if we look back to the specific heat supply map, we can see that it is not as good as A and A2. So what we can say is that there's a trade-off between the heat supplied per mass and the coefficient of performance of reactive fluids based on this study. So one solution, or one way to see how an inert heat pump compares to a reactive heat pump, is by calculating the mass flow rate that is required for the reactive heat pump in order to supply the same thermal power output in kilowatts as A2, which is the better performing inert fluid. So here, for example, in the x-axis, you can see the coefficient of performance of the reactive fluid compared to that of A2. And here the mass flow rate that you would need for your reactive fluid compared to that of A2. And each point in the scatter plot is a different fluid. The blue region is all the fluids that will give you at least 10% increase in the coefficient of performance, where you have to increase the mass flow rate by multiplying it by 10, a factor of 10 or less compared to A2. So this is it. And of course, the lower boundary of this region gives you the lowest factor that you need to multiply your mass to obtain this increase in the coefficient of performance versus A2. But it shows us really that you can get double the coefficient of performance if you just multiply the mass flow rate by less than 2, a factor of less than 2. Here, I present the temperature entropy diagrams of the heat pump cycle. You can see in the middle, there's a high-performing working fluid, reactive working fluid. On the left, you have inert A2, which is pure no reaction. On the right, you have inert A, which is also pure no reaction. And you can see that, first of all, the isobar shapes are different because of the chemical reaction and the composition change. But also, you can see how the heat pump is more efficient because it is approaching the Carnot heat pump, which is a square on the TS diagram. So now I'm going to present briefly the results on a real vapor compression cycle. Now the application is not low temperature, but high temperature. And for that, of course, you can see the valve as an expansion device. The temperature of the heat source is at 80 degrees Celsius constant. And the temperature of the heat sink is at 130 degrees Celsius. The pinch point of the two heat exchangers is taken to be 10, and the pressures in the cycle this time are not fixed, they are optimized or selected to optimize the coefficient of performance. And so the pressure drops are neglected because now we're comparing two different fluids, and the compressor isentropic efficiency is taken into account. So what is the thermodynamic model in this case? And the fluid is modeled as a mixture of the dimer and monomer using the Peng-Robinson equation of state, but also using the chemical equilibrium to determine the composition of the fluid. And the fugacities, they come from the equation of state in this case. You can learn more about the thermodynamic methodology by visiting the following articles that I'm attaching here. So the fluids that we are going to compare are reactive N2O4, which I already spoke about in the intro, versus water, which is now considered the state of the art for a high temperature heat pump, or the best fluid that's available, safe, and cheap. Okay, so here I present the temperature entropy diagrams of water on one hand, and N2O4 reactive on the other hand. And we can see already a few differences, multiple differences. In fact, for the water, you have the minimum pressure at 0.3 bar. This is a subatmospheric pressure. It induces problems with the heat exchanger design on the heat source side, and the compressor also, because the specific volume of the fluid will be large because of this low pressure. For N2O4, the minimum pressure starts at around 7 bars. For the maximum pressure, 3.6 for water and 63 for N2O4. However, the pressure ratio required in the N2O4 cycle, the reactive N2O4 cycle, is lower than that of water. The thermal energy, specific thermal energy of water is higher, and that's expected because the latent heat of vaporization of water is large compared to a lot of fluids. And at the end, the coefficient of performance, which is the main interest in this comparison, it is 5.3 for N2O4 and 4.1 for water, which means 29% increase in the coefficient of performance. So this is huge in terms of efficiency, environmental footprint, and costs. So, however, the problem with N2O4 is that it is toxic and corrosive. So in conclusion, we can see that reactive fluids offers significant potential to increase the thermodynamic performance of heat pumps compared to inert refrigerants. That is because of both compositional and thermal effects of the reaction inside the cycle, which happens spontaneously without, ideally without external stimuli. And there remains a need to find other reactive fluids that offer high performance like N2O4, but are safe and environmentally compatible. So the next steps at NEEXT and LRGP is to evaluate the thermodynamic performance of all the patented fluids that I talked about, and to understand the effect of the chemical reaction on the heat transfer in the heat exchangers, because this is really important. So how it affects the sizing of the heat exchangers as well. And of course, to conduct a more advanced cycle optimization with temperature glides of the heat sink and source and more complex cycle architecture with the intercooling, for example. And this is already a work in progress. So that's it from my side. Thank you very much. And this is like the QR code for my LinkedIn.
Yeah, thanks a lot, Aya, for this very interesting and good insight into the reactivity working pairs. So my first question is like, if you introduce a reactivity in the working pair, how about the operation? I mean, it will be and the optimization, it will be highly dynamic, no? So is it a challenge to really bring that to industry, or isn't that such a hard topic?
I mean, it depends on the application, and it depends on the fluid. For example, if you have a certain application, you can go and assess a reactive fluid, for example, and you can see how the kinetics, because infinite rate of reaction is not really a real assumption, and you can see how the kinetics would affect the performance inside a real application. And then you can see if the reaction time is less than the time that you require in each device or thermodynamic transformation, let's say. If it's acceptable, then we can assume that the reaction is taking place spontaneously on its own inside the cycle, and this is passive without active interference. And so you can either fix your application and go look for the reactive fluid, which will give you the composition you want in certain locations inside the cycle, or do the opposite, where you pick a fluid and you can test it on different kinds of applications to see that, yeah, it will be in the right composition with the right thermal effect and this kind of cycles, and then this is what you basically have to do. But
Okay.
so it could be a passive operation without active control.
Good. And related to that, so you talked a little bit about the safety issues of the working pair that you have shown. So do you work on any other working pairs that are not that dangerous?
Yeah, of course. Well, in the patents, there are hundreds of reactive fluids, so these pairs, and each of them are now being studied from both a thermodynamic point of view, which is what I'm doing now, but also from a chemical point of view, which is the work of my colleagues, and who are assessing the chemical stability as well, the toxicity, the corrosion, the environmental safety.
Okay, great.
Yeah.
The last question is from Jean-Charles. He asked, or he wonders why you limit yourself to positive values for enthalpy and entropy, or maybe that was a misunderstanding, or so we
Yeah,
saw
yeah, I
mainly positive.
understand. Yeah, actually, what you see on the x-axis and y-axis as positive values, these are the values for the forward reaction.
Mm,
So
okay.
because if you go back in the opposite reaction, it will be the same value, but in the negative sign. This is why we chose to show the positive value. That's it. Yeah.
Okay, great. Okay, thanks, Aya. Thanks a
Thank
lot.
you.
And now we give the word over to Arne Speerforck. So Arne is a professor for technical thermodynamics in Hamburg at TUHH, so it's the Technical University of Hamburg. And he is really an expert, and that's why I'm very happy to have him here, giving insight about his impressions on heat pumps, because he has been working before he was becoming professor. He has been working in Weiland. Weiland is a very big company working on heat pumps in Germany. So to give you an impression, you may know the chemical company Covestro, and Weiland has the same number of staff. And so it's really amazing and a big company, and you see how big the topic is in Germany. And yeah, Anna, I'm looking very much forward to your talk. Please share the screen, and then I hand the word over to you.
All right. Thank you, Christoph, for that introduction. Can you, I should right now be able to see my slides? Is that true?
Yes, yes.
All right. Yeah, then thanks for introducing me and for having me here. As Christoph already said, I was working in Weiland Group before I became professor for engineering thermodynamics here at Hamburg University of Technology in 2021. And yeah, it's my pleasure to talk today about heat pumps, technology direction and research directions. And as I saw that Andre will also talk and probably talk more about larger heat pumps and also mixture applications for industry, I decided to limit this talk a little bit to the to more household appliance level and also to R290 or propane heat pumps, and show you what's going on there in this size area. So let me quickly start with why I do believe that heat pumps are an important part in the future. Is that if you look at this slide, you can see that on the right-hand side, there is projections for the global demand for heating and hot water and also for cooling. And you can see that from 2018 to 2050, it was projected that basically the heating demand will even slightly decrease, which is related to modernization and also global warming a little bit. But you can see that the cooling demand, as you see here, will almost triple. So it's reported by the International Energy Agency. And you can also see that also in mid-Europe or countries with more mild climate, people are also looking for air conditioning. And I believe this really makes heat pump also an interesting solution besides just decarbonization, because a reverse cycle heat pump can provide heating and cooling at the same time, making it even more promising and economically feasible. You can see that the sheer size of this energy demand, if you compare these dots to the final energy demand of Germany, you can see that this is really a large issue for tackling climate change and responding to that. Now, also before I tend to focus more on the technology, I also want to talk a little bit about the status and the market. Obviously, heat pumps are an obvious solution for the energy transition. When I was working in industry, which was around this area, I was heading the pre-development technology department for heat pumps, and you could in this area feel that it was a kind of a Me Too product, so you would manufacture it, but the big boom was still to come. And then you can see that years later, you could actually see this boom. So in the market, those are the units sold in Europe added up. So this is 3 million. It's the largest one. You can see that now in recent years, it went down a little bit. It's maybe associated to discussions going on in Germany. And what I always also believe is interesting is that if you look at the type of heat pumps, so this blue one are air water, air heat pumps. Ground source heat pumps are just this small green area. So even though from a thermodynamics perspective, ground source heat pumps make a lot of sense, they play a smaller role, let's say, in the markets. And if you then look at the main challenges for household appliances, it was mainly at that time also the F-gas regulation. I think you all know about that. It's a phase out of fluorinated gases or gases, basically refrigerants with a high global warming potential. And basically, as this happens, so as the amount was reduced from 39 to 63%, there it really shook up all the manufacturers because the price for the common refrigerant R410A went up a lot. So they all looked for alternatives. And the problem is that it's not that there are no alternatives, it's just that mostly alternatives are flammable and or toxic. So you need higher safety requirements for these household appliances. I think Andre pointed to that in industry you might have lower requirements, but if you manufacture like 3 millions, they need to be safe, and you need to take care of every kind of use case or misconduct which is possible. And also, I will later give a small outlook on the electricity infrastructure required. But let us now first start and talk a little bit about the refrigerant for household appliances. And I think there's a very still read-worthy paper, even though it's kind of some years ago, by Carmen from 2008. So he separated the refrigerant used into 4 generations. The first generation was whatever worked. So there you were not competing with other technology than ice boxes, and you were using whatever worked as a refrigerant. And interestingly, in this area, propane was also a refrigerant of choice because it was available. And you can see this is an advertisement of a company made in 1922 by the Car Lighting and Power Company. And they marketed propane as the odorless safety refrigerant. As you can see here, it is neither deleterious nor obnoxious and should occasionally require the engineer can work in its vapor without inconvenience. So you can see at this time, the look on propane was more from that side. And then also other refrigerants were used, let's say sulfur dioxide, heavily toxic. So this required a change. There's a citation that if the refrigeration industry would try to go anywhere, they would need a new refrigerant. So the focus after that area was more on safety and durability. So the way people screened refrigerants was they look for a normal boiling point, so not as sophisticated as today, between minus 40 degrees C and 0 degrees C, and looked for it to be safe and non-toxic. So and then people came up with this mostly associated to fluorinated gases, which were then, or also chlorinated gases, which are then, let's say, characteristic for this area here. Then the ozone protection phase began. So the focus was to get rid of gases which were responsible for ozone depletion. And whenever I tell this in a lecture, I always tell students it's also a good sign because here a change was made. These high ODP refrigerants were banned, and you could really see there is an impact. So it's maybe a good example for what's coming now. Now the focus is on the global warming or low global warming refrigerants. And as I said, again, there is good refrigerants like propane. And we're coming back to this first area where it started with this advertisement. If you have a look at propane as a refrigerant, it's very simple to explain that it is basically a very promising refrigerant from its thermodynamics. So what you can hear is the saturation vapor pressure of different refrigerants, mainly compared here to R410A, which was the standard refrigerant. You can see that R290, which is propane, has kind of a flat curve here. So it means that you can have a comparatively high temperature lift by comparatively low pressure lift. So this is beneficial. Another point of propane is that it has a kind of comparatively high latent heat of vaporization. So these quantities are all evaluated for saturation pressure at 13 bar for the different substances. You see it has a high latent heat of vaporization, but as you know, the Clapeyron equation, you have a flat curve here, so low dP by dt, and you have a high enthalpy of or heat of vaporization, so you need to pay somewhere, and you pay with a comparatively low vapor density here, which makes kind of propane equipment a little bit more costly because you need to, this is the vapor you need to compress. And if the density here is low, you need larger displacement volumes, so you need larger equipment. But you can see very quickly that propane is basically a very suitable refrigerant. Now, if we look at research, this is basically a chart from a review published recently by the group of Eckhard Groll from Purdue. They analyzed different scientific review papers who looked at hydrocarbons as refrigerants, and you can see that there was quite an amount of reviews papers published in the recent years. And you can see that they are basically clustered as following. So people look at flow boiling, flow patterns, and heat transfer. So these are mainly the upper three papers here. There is still, let's say, a need, I think, to look at heat transfer characteristics as well, especially for mixtures. I think here's not a lot or a large database, which is mainly due to the safety requirements for the labs, I believe, but also for flow patterns of mixtures or also refrigerant oil mixtures. Here, in the second area, the people looked more general on hydrocarbons as refrigerants, so with all different kind of aspects. I will come to that in a second. And also the standards associated with this play an important role. Because you now need or obviously have different need for safety and flammability considerations. And a large point, also an area where we are working on here, is the charge reduction. So you want to develop refrigerant circuits with less charge, because if you have a refrigerant which is flammable or toxic, it is always better if you need to have less of it in your cycle. If you cluster all these papers together, you can see that people are one side working here obviously on heat and mass transfers and also on properties and cycle characteristics, which would also cover what Andre was talking about. So you try to find mixtures, you find different flow sheets and cycle characteristics. Another big part is material compatibility. People there are mainly looking at refrigerant oil mixtures, so the compatibility of, let's say, different refrigerants and oils. Flammability and safety considerations, system performance is obviously, and also charge minimization. And you can see that there's also still interest from fundamental research. Those are just coordinated programs which are financed by DFG. So you can see that there's currently one research unit for oil refrigerant multi-phase flows and gaps with moving boundaries, novel microscopic and macroscopic approaches for experiment modeling and simulation. So this is largely about oil refrigerant mixtures. It's run by Markus Richter, our colleague, and they are looking into mainly the topic of oil refrigerant mixtures and the behaviors in compressors, or also the thermophysical properties. Another research unit is currently looking at flammability and safety considerations. So they are mainly looking at reaction kinetics for fluorinated gases in this area, how they burn and how they are ignited. And also there's a priority program by DFG, which is focusing on Carnot batteries. And I think their research on heat pumps is also included and covers nearly all these areas, because there are also different areas. But let me quickly focus in this talk a little bit about these aspects here. I will have a look on material compatibility. So I show something about heat transfer related to oil refrigerant mixtures. I also look into the charge minimization system performance topics a little bit. The problem with charge minimization is actually, as I said, directly associated to the safety concerns. Now, if we have toxic refrigerants or flammable refrigerants, we want to have a low charge in it. And these are basically results where people also from this recently published review, where people looked at the different refrigerant mass distribution in the components. So basically you have here a compressor, you have a condenser and evaporator. Here's a liquid line. So this is a ductless split system. It's basically a thing you all know. You have one outside unit, one indoor unit. In almost all hotel rooms have these kind of units. So you can see that there's a large fraction of the refrigerant usually here in the condenser because of the liquid part of the condensed refrigerant in it. The same is true for also liquid to liquid heat pumps. Here you can be a bit more, or you can have a little bit smaller volume. So refrigerant charge here is a little bit less usually. Also here, the heat exchangers play an important role, but also in the compressor. And in the compressor, it's also a part of solubility of the refrigerant in the oil. So also an interesting point to look at. But this is in general the charge distribution, and it's very kind of tough to measure that. So if you want to do experiments in this area, I was working in Maryland as a postdoc with Reinhard Rademer for a while, and there we also were doing running tests on this, and there, let's say, kind of a lot, at that time 4 students were in the lab to what they did is basically at the same time they closed this quick closing valves by hand. So at a certain point of operation, you just shut these valves down, and then you measure where actually which mass on refrigerant is. And currently, or a lot of our products is liquid nitrogen method. So you shut down these valves and you measure the refrigerant mass in the condenser, for example, by just connecting it to this container with a very low pressure due to this atmosphere. And then you weigh later this container so you can determine the mass. But this is very cumbersome. It takes quite a while to do one measurement. It's 1 hour to 4.5 hours. So it's quite hard to work on that and accordingly work on charge minimization. And there is one thing we are currently working on here. This is a test rig we built for charge reduction, but we want to do it via online measurement. So basically what we are building here in the setup is that we have a pumped cycle. So we don't use a compressor here. It's just a pumped cycle because we don't want any vibration. We have 2 Coriolis meters to have a broad range of mass flow. And then we condition the propane to a certain level. Here we could evaporate it. And then we have here our test section is right now for condensation. We have 2 quick closing valves. And here we have some hose to connect it to the rest of it. And then we want to measure within this test section, we want to measure heat transfer, so condensation. But at the same time, we want to measure the mass of the refrigerant within the ductwork or in the pipe works. So we built for that a test rig. You can see that here basically. So I took that photo yesterday by myself. I feel I am not a good photograph, but you can see here that we connected this test section here. It's connected to 2 hoods, and then we have it here on a scale with a counterweight. And then you can basically measure here the weight of the refrigerant flowing through that. And it took us quite a while to make that work because it's kind of cumbersome to have it so disconnected that you can measure these small amounts of propane in it. But here is one preliminary result I want to show about that. You can see here that we varied the pressure. So basically at this high pressure, propane should be liquid, 1 phase. And at the low pressure, it should be 2 phase. And you can see here what kind of mass we measured in it, in this pipe. So you can really see that we were able here to measure online the mass of propane in it, because this is here, it's a higher mass, which should be the case if it's a liquid in 1 phase. And you can see that it's also reproducible. So we were measuring constantly the same mass when we had this higher pressure. And at this lower pressure level in blue, you can see is that the mass was reduced. It was then 2 phase. And you can see that it's also reproducible. So this is very promising. And here we validated this by closing the quick valves, dismounting the condenser from it, and comparing it. And online we measured 27.41 gram, and offline we measured 27 grams. So we had a very small deviation of 1.5%, and are now happy to contribute here by delivering, like, let's say, more advanced geometries for charge reduction, which is then up of our current work. And another example here I want to provide, because this is more a thing where we want to look more at more complex structures, but it can also be way simpler than that. And as I am also from industry, I want to highlight one point here. This is now an example for mobile heat pumps. We basically work together here with a large car company. And this car company approached us and they say, okay, we use this refrigerant, it's Y1234F. And there also charge reduction is a large topic because it's also, when it burns, it can also become toxic. So you don't want a lot of charge in it. And they approached us and said, okay, we model our whole cycle, but we cannot really make the model work. So it does not fit to our experiments. So the first statement they made was, okay, we have here these experiments. This is a very simple 1D analytical simulations and also a CFD simulation of just the pressure drop, let's say, through this cycle. And they say, okay, we cannot really make this work. And then we had a look at it and looked at the model, and they basically started off classically with a 4-component model. So they modeled the compressor, condenser, evaporator, and the throttle valve. But then we had a closer look and we find, okay, well, first we need to take these lines into account. And what you can see here is a liquid line which would be mounted beneath a car. So this is kind of adjusted to a design of a car. And you can see that this liquid line here has a specific form. And we then thought, okay, the measured, the experimental values are way higher than the ones measured in reality, or the ones simulated. And then we had a look at it and investigated it. We did some closer, or we did some work. Finally, we found out that it's just the way they manufacture those liquid lines and they connect it. So they were connecting it by pressing it together, as you can see here. And they were calculating with this geometry. And obviously the pressure drop induced by this is way larger. So you can see here, this is a scan profile, and this is the CAD file they used, and they also provided us. And you can see that this obviously has a way different impact. And by this, we proceeded. So we did a very simple model of that to calculate the pressure drop through that. And we could see that finally, we could reduce the pressure drop, or we could find out that 85% of the pressure drop in this car cycle was just done by these transition pieces. So it's like a large amount, and this means also because you can just do this liquid line, which contains a lot of charge. You can just reduce this diameter by a lot, and this means you can reduce the charge in this case by roughly 45%. So it makes everything way safer and way better. So this is also a point. It looks very simple, but also in practice, this is very important to consider these liquid lines and also the rest of the geometries for that. If you look at these charts, you can then see we calculated you did the CFD calculation, and then we calculated the pressure loss value of this transition piece. If we then did it with very simple one-dimensional models, you can see that we met the experiment quite well, while these are still the uncalibrated CFD data. So this works quite well, and you can really achieve a huge amount of charge reduction here. Then let me come to another point, which is also always important connected to charge reduction. I also pointed to this research unit, which is organized by Markus Richter, where they look into refrigerant and oil mixture properties. So this is from the PhD of Marco Mörle, who recently graduated at the University of Rostock. And you can see here that he looked at the heat transfer characteristics of oil and refrigerant mixtures. This is also important because if you use hydrocarbons, then the oil, which is used for the compressor, will also circulate through the whole circuit. And you can use way smaller diameters if you don't have any oil. So you can use microchannel heat exchanger or whatever. But the oil requires, let's say, a bit larger diameters. And if you look here at the heat transfer impact of oil, you can find that oil has a large impact when you have high performance surfaces. So this shows for different saturation pressures, the impact of the basically, this factor here covers the whole heat conduction problem from refrigerant to secondary fluid. And you can see it decreases from 1 to by roughly 20% if you have a bit more than 4% oil in there, which basically really limits your heat transfer. And in his work, it is shown that this is really heavily depending if you use high performance pipes. You can see here they have very structured surfaces. So you have a lot of nucleation sites on the surface, and the oil will block these nucleation sites. So if you have high performance pipes, the oil will directly decrease the performance of the cycle. And that is definitely very detrimental to that. And another thing which is also required for these mixtures is still obviously the thermophysical properties. So all the people who work in this area, I think there's still work required to describe that. Also the transport properties and also the flow patterns. For example, if you look for oil recirculation, the flow patterns in the suction line of the compressors to get it back to the compressor is also very, still I think unclear. And also the research from fluid mechanics, I think, is still required. And as I already mentioned, Reinhard Rademacher, for whom I worked in Maryland for a while, when I was new here at university, I was talking to him and told him that I'm also thinking of working on oil refrigerant mixtures. And he told me it's not required because future compressors will definitely be oil-free. I'm not sure if he will be correct very quickly, but EBM Papst, the German company, by now, I think in the last year they published and highlighted that they have now a propane-capable small turbo compressor in the range of 3 to 10 kilowatts, which is actually oil-free. So this could be potentially very important because it could really enable smaller diameters and less charge for propane heat pumps. And then there's another slide here I want to show, basically just because I think it's usually interested for a broader audience. It's just to show where our current appliances right now standing if you looked at the sheer level of the technology. So this is basically from manufacturer sheets evaluated. So for 4 different manufacturers, which are not disclosed here, so to say, but for a temperature level between 7 degrees C air temperature and 35 degrees C water temperature. And what we highlight here is basically the COP, the real COP related to the Carnot efficiency, because this is like a limit for where this technology right now might be standing. And we always consider, while doing that, we consider 5 Kelvin for to drive the heat transfer between evaporator and secondary fluid, also condenser secondary fluid. And you can basically see that you achieve values here between 0.5 and 0.6. So there's still room for improvement, but they are here already, approaching a higher level. And if I talk to students, I always tell them, well, calculate with a efficiency factor here of 0.55, and then you can quite accurately predict the behavior of today's heat pumps. Another point which I want to make is I also want to highlight the one problem I still see. I mean, I'm working on heat pumps basically my whole professional career, but I also want to show that I believe we have still an issue is that if you look at the simple provision of heat pumps, so to highlight here an issue we could have is that we think if you would supply basically all the amount of energy and especially power, so then you require for heating and hot water by heat pumps, then it will cause pretty high electric loads. And we did a simple example. We develop a library here for sector-coupled energy systems. It's transient for Modelica, and you can see that here. What we did is we assumed a simple ambient temperature here. It's a period from January to February with data from 2018, because then we have all data available. And you can see that here the ambient temperature is highlighted in black, and the COP of a heat pump in a conservative manner assumed is highlighted in gray. And you can see that obviously the COP is lowest when it's the coldest days outside. And if you would cover all the energy required for household heating and hot water in Germany, you would reach here a peak demand of 90 gigawatts. So if you just simply assume you have no storages here and power all the heat pumps at the same time, and if you compare it to the actual data of this year, then you see here that the electric peak load in this year was 79 gigawatts. So the peak load adding up to that is quite large, and the maximum supply of renewables, obviously that changed quite since then, was 59 gigawatts. But you can see that you really have high peak loads on this grid. You would need some more solutions for maybe molecules to store, or also thermal storages to cover that. So this is our last point actually I want to mention. And yeah, I thank you very much for that. And for me, that would be it for this talk. Thank you.
Yeah, thanks, Arne. That was also another very important view on the heat pumps, and thanks very much for this insight and sharing your view. My question, or what came into my mind when I was listening to the other two talks and now listening to your talk, what's your view? What's your opinion on, I mean, in the last slide you showed like there is a gap between the energy, the electricity that we have, and that would be theoretically used for heat pumps. But there are, like Aya and Andre showed, that there might be mixtures, or they might be reactive working pairs that could increase the COP. Is the industry open for this?
I think they are open for that. I think for me, one practical limit for these household appliance level was that for one point, as Andre also showed, that the temperature lifts are maybe more moderate. This is one point, and the two other points were that simple, if you have a leakage in the field, then what do you refill? So, I mean, if you have a mixture, it's not so easy to refill the right component. And then the last point is that frosting is also for most air source heat pump an issue. And if you have a zeotropic mixture, for example, you will have also very different frosting behavior of the evaporator, which requires, again, engineering. So I think this makes people a bit reluctant to that.
Yeah,
But
that's true.
still, I don't think I wouldn't say they are not open. People also look into it.
Okay, if you talk about the leakage, is that a really serious problem, or?
I would say that I'm not sure if it's very serious. It is a problem. So people need to refill appliances, and also it's a problem because you have so many in the fields. But usually, I mean, especially if you use propane, you don't want anything to leak. So you will try to avoid that by any cost and limit these cases. So I don't
Sure.
think this is the main reason to hinder it.
Sure. And the example that you've shown on your last slide, that was also with the propane? So was it the heat pump with the propane?
So you mean the system, the
Yeah.
system view of heat pumps? Oh no,
Yeah.
that was a very regular analysis for a COP. There, I just wanted to highlight the
Ah,
point that and the COP I think was chosen optimistic. I just wanted to highlight that if you apply heat pumps everywhere, then you have high loads on the grid.
I
That's
see.
just it.
I see. Another
Andrea has his
Andrea,
hand
please,
raised. Yeah.
May I say something?
yeah.
sure.
And to the last slide, because actually, Arne, I was semi-happy about that slide, because I think it's also, I think one clearly needs to say, I think it was quite an extreme scenario
Yeah.
Yeah, and putting it out there because I think it really shows, I don't know, people can steal that slide and say, oh, see, this will never work. Yeah. I just want to maybe give some more perspective. So I think you really choose an extreme case to show the numbers are enormous. Yeah, but I think also in practice they go down. You showed kind of it's about integrating storage. Everybody who gets a heat pump gets a storage kind of, and so I think there's a lot of elements. And actually, we did very detailed studies for Switzerland, and where you show really, I think one is important that energy demand goes down because people say this electricity goes up. But if you look at the energy system, because the heat pump is so efficient, we use less energy in the system because you do not burn fossil at your homes. So energy goes down, the numbers, I think that's important. And I think one thing is maybe that adds to this, heat pumps may have an important role as flexibility, which providers, which actually can generate additional benefits. So I think it's an important point, similar to my little study on the chemical park. We need to look at these and the systems, but I just want to say this people might have read a very negative thing. So don't employ heat pumps stupidly, but then they can even provide value to the system, but we need to plan them within the system context. I apologize for stealing time, but I felt it was important.
No, Grazia?
Yeah, I would like to thank the speakers because they really highlighted the importance of thermodynamics. So I think this was one of the spotlight talks with the strongest thermodynamics content. And I have just one final remark because we always like to leave a message to, especially to early career researchers. If you were to suggest an open challenge to a student starting their PhD career or the research career, which one would you recommend? What do you think is the most promising, but also challenging, open question in the field of heat pumps?
Yeah, if I start, I would I would advise maybe to look in different kind of cycles. So today I talked about vapor compression heat pumps, and we also focus on that. Maybe also solid state. I also think thermoacoustic heat pumps are interesting. So I would personally like to look into that as well.
Okay, thank you. Christoph, back to you.
So honestly, I would have gone in the same direction. Particularly if you start your career, if you think about a PhD or something doing science, I would simply say go for the excellence in science, and I think really try to push the frontiers. And that's maybe more in try to come up with a cycle. And actually, even if it does not fly, yeah, maybe you end up in a company like Aya, kind of try to push it, bring it to the market. But I think it's about I think we really have to map out the space. The challenges are enormous, and maybe you will not single-handedly solve the energy transition, but there might be niche applications for some of the technologies Arne mentioned, like thermocaloric. There's so many things going on at the moment, and to understand these systems, how to transfer your thermodynamics into this, and see then the real-world constraints during this feedback loop. I think it's a great area to be in.
And if I may add also another thing, this is, I mean, a little bit related to chemically reactive fluids in general, but you have this in real life, you have the kinetic component, which affects how accurate the thermodynamic models, which don't take into account any time dimension. It affects how accurately they represent the reality. So coupling these two, so the kinetics with the thermodynamic model to represent or to model cycles or processes would be also an important aspect.
Great. Okay. So maybe with this we can close this webinar, and we have seen today and listened to 3 exciting talks covering like physical mixtures, chemical mixtures of heat pumps, even hydrodynamics, and big, really deep insights on the technical implementation of heat pumps. And I think that shows you. I mean, we teach students in the 2nd year heat pump cycles, right? So, and you see there is so much room for improvement for science, but also for industry to stick on what we do and what we find. And I think this is a very nice exercise to do. And Grazia, also your suggestions, I think is pretty nice. Yeah, with this, I think we can close this webinar. Thanks to all of the speakers again. I really appreciate it and hope to see you soon.
Thank you.
Thank you so much. It was fun.
Bye bye.
Bye. Thank you.
Bye.